Okay, so this is 8.1, Matrices and Systems of Equations. So this is a good introduction to what a matrix is, how it can be used, and then I'm going to demonstrate how you can use technology on your assignment and the kind of work that I'm expecting you to show when you are doing that. So that way you know that you're showing enough work. So 8.1 covers writing matrices and determining their dimensions, performing elementary row operations on matrices, using matrices and Gaussian elimination to solve systems of equations, and then using matrices and Gauss-Jordan elimination to solve systems of linear equations. So you already know Gaussian elimination. It's the same idea but in matrix form. And then there's also Gauss-Jordan elimination. So we'll talk about those differences. So let's get into what a matrix is and how this connects to systems of equations. So a matrix is a way to write an equation without variables. So you take your system of equations, which I have here on the left. We have two equations, two variables, and what you do is you basically write it without the variables, without the symbols. So you are just writing the numbers. So a matrix has brackets. So these brackets on either side, these are required to indicate that you have a matrix. So if you're typing up your work, you need to include those brackets because that is part of the notation. This dashed line, that is basically showing where the equal sign is. That is not required, but that is usually helpful for a lot of people so they can keep track of which side has the variables, which side has what it's equal to, basically. Writing matrices this way is really nice because you don't have to worry about the variables, and this is used a lot when you have programming and a lot of data science because you have tons of equations, as I mentioned yesterday during my introduction video. And if you're trying to do that on a computer, storing an equation with all the symbols, the variables, that takes up space. And if you can ignore the variables, ignore the symbols, and just store the numbers, that's less that you're storing. And so that actually saves you space in your memory or on your hard drive. And so it's a more efficient way to store the stuff. And so when you do programming, a lot of things that you do are done with matrices because it takes up less space. It's a better way for storage. So it allows you to condense your work. A system that we write as a matrix is called the augmented matrix. So that is the name when you take your system and you convert it to a matrix and you're including what it's equal to. If you ignore the part after the equal sign and you just have the left side with just the variable portion and their coefficients, that's called the coefficient matrix. Now some additional matrix vocabulary. So your matrix has lots of entries. Each number in the matrix that's an entry are also called an element. And so you always refer to its position based off of the row and column it's in. And it's always row first and then column. So A with the subscript 2, 3 means that it's the number in row 2, column 3. So that's how we identify the locations of the numbers. And if you're in programming, that's essentially how you identify it when you program as well. If you're going to have like an array that's more than just a row or more than a column. If it's a 2D array, then you always do row and then column. The dimension of the matrix is always row times column, row then x column. And the rows are always called m, the columns are n. So it's always m by n. But they could be the same number. So if you have the same number of rows as columns, it's called a square matrix. Otherwise, it's rectangular. We also have what's called the diagonal of a matrix, and that always starts at the top left corner. So wherever that is, you can have a diagonal of a rectangular matrix and a square matrix, but we usually only care about diagonals when we have square matrices. A matrix that has only one row is called a row matrix, and then a matrix that has only one column is called a column matrix. So this is just various vocabulary to understand matrices. So we've already talked about the elementary row operations. I went over that in 7.3. What's special here is that we're showing the notation. So I used a little bit of this notation. I actually So I don't use this exact notation. So when I interchange two rows, that is that is great notation there. And I'm actually going to zoom in so you can see this a little better. So if the first row is A, the second row is B, you just are putting an arrow in between them to show that they're switching spots. So if you're multiplying a row by a number, I put that number in front of the row number. So I don't use capital R's, I use lowercase, but it's the same thing. And then if I'm replacing a row with that result, I'll put an arrow towards and then the row that I'm replacing it. And then it's the same thing. If I'm adding row to another row, then I will show it with the plus sign here. So I do use basically this notation. I don't use capitals, but it's basically the same thing. And I mentioned this a little bit when we were talking about the Gaussian elimination last week, about how you get a lot of calculations and it's very easy to make a mistake. So the book has a remark here to make sure you write down each step that you perform so that it's easier to check your work. I also recommend just using technology because then you don't have to worry about arithmetic mistakes, because in the real world, we rarely do matrices by hand. We use computers to do them. Last week, when we were talking about systems of equations, I did a session on 7.3, and that's where you were introduced to row echelon form. And so as a system, your first row would be x plus y plus z, or whatever your numbers are in front of there. So in this case, by plus z equals d. Your second row wouldn't have x, and it would just be y, and you'd have a coefficient of 1 in front of your y. And then your last row would be just the z with a coefficient of 1, and then you would back substitute into the previous row or the previous equation, and then you take those two answers and you put them into the first equation. That was row echelon form. When that is in matrix form, those blank spaces where you don't have a variable are zeros. So you end up with ones. Come on, it doesn't want me to draw right now. There we go. Ones in your diagonal, and then you have numbers above the ones. And that's row echelon form, and everywhere underneath the ones you have zeros. Now there is a version of row echelon form called reduced row echelon form, where you have zeros above and below. So you have zeros only in the diagonal, and then the only other numbers are to the right, where your very last column, where your answers are. And so to the left, you have what is called the identity matrix, where everything is ones in the diagonal, everything else is zeros. So your coefficient matrix is the identity matrix. When we look at this in system form, this would be x equals d, y equals g, and z equals j. So you have only one variable in each equation. You basically have the answers right there. So the two different forms for solving, we have Gaussian elimination, and we saw that's what gets you the row echelon form. So that is Gaussian elimination. Now, reduced row echelon form, that is used when you have Gauss-Jordan elimination. So basically, this guy with the last name of Jordan took Gaussian elimination, took it some steps further, and came up with reduced row echelon form, and so they named it after him. That then is Gauss-Jordan elimination. So you can use either one. You can solve with Gaussian elimination or Gauss-Jordan elimination. I spelled elimination wrong. I did this the first time I recorded this as well. Let's try this again. Apparently I really don't want to have some extra syllables. There we go. I personally put my stuff in Gauss-Jordan elimination because I find it easier to just read the answers rather than doing the back substitution. So for both of them, you're using row operations. It's just when do you stop? So a Gaussian elimination, you stop when you have ones in the diagonal. So I mentioned that the diagonal, so you want ones in the diagonal. Gauss-Jordan elimination, you stop when you have ones in the diagonal and zeros everywhere else. If you look at that, the coefficient part there, the coefficient matrix, which is the left part, that is called the identity matrix because it's just ones in the diagonal, zeros everywhere else. So that is a special type of matrix. It's a square matrix, ones in the diagonal, zero everywhere else. So that's what makes it reduced row echelon form, and that's when you use Gauss-Jordan elimination. So for Gaussian elimination, you have to do back substitution to find your answers. Gauss-Jordan elimination, all you have to do is look at the last column, and that's telling you your answers. So whichever one you use, it's up to you. You can use either one. When I did matrices by hand, I always did Gauss-Jordan elimination because I like to just read the numbers off on the side. But whichever one you do is up to you. So I do have a demonstration on a two-variable system. This is actually the same system I used in my Gaussian elimination example. It doesn't hurt to see the same example again. And I'm going to be doing this on the fly, so hopefully the number of steps I used in that system to solve that one is going to be the same here, but we will find out. But first we need to put this in matrix form. So in matrix form, you just look at the coefficients. And then I usually don't bother with that dashed line, but if it helps you see where the equal sign is, we can put that there. So to take the system to a matrix, we have -2, 3, and 10. And then the coefficients on the x and y are 1, 1, and then we have 0. So my goal is I'm going to do, let's do Gauss-Jordan elimination, where we have ones in the diagonal, because you've seen Gaussian elimination, so let's do Gauss-Jordan. So I want to get ones in the diagonal, which means that I want to, let's see, first I want to get that -2 in the top left to be 1. So I could divide everything by -2, but that's going to give me some fractions. Or what I can do is make a 0 in the bottom left corner there in position 1, 1, or row 2, 2, 1. And I think that's probably the easiest thing to do. It would be easiest to make that bottom left 0. And so in order to do that, I need to multiply row 2 by 2. So that way, -2 and 2 cancel. I'm going to take 2 times row 2. I'm going to add that to row 1. And then I'm going to store that. That result is now going to be the new row 2. So that's the notation that we use when we do matrices. So I like to, a lot of people try to do this in their head, and that's prone to mistakes. So I'm going to first take 2 times row 2 and write it. So that would give me 2, 2, and 0. And then I'm going to put row 1 underneath it and then add those together. So that gives me 0, 5, and 10. So now I'm going to write my matrix. First row has not changed. And then I'm replacing my second row. So I have -2, 3, and 10. And then 0, 5, and 10. Okay, so that second row, my goal, I want to have 1 as the second element in the second row. So I want that 5 to be a 1. So to do that, I can divide everything by 5. Now, we normally write this as a fraction because we always write this in multiplication. So I'm really multiplying the second row by 1/5. And then I am replacing the second row with that result. So I can actually, that one's simple enough to do in my head, because I'm basically just dividing it by 5. I'm not doing anything complicated. So my first row is unchanged, but now my second row is 0, 1, and 2. So far, I have my bottom row exactly the way I want it. So my next step now, I need to get rid of, let's make that 3. We want to make that 0 up there. So I'm going to have to multiply the second row by a -3 and add that to the first row, and then replace that first row with that result. So I'm going to take -3 times row 2, add it to row 1, and then I'm going to make that the new result for row 1. So -3 times row 2. So that would be 0 times -3, 1 times -3, and 2 times -3. So that's the second row. So that is 0, -3, -6. I'm adding it to row 1, which is -2 and 10. So that gives me -2, 0, 10 minus 6 is 4. So now my matrix, and I'm replacing that in row 1. So now I have -2, 0, 4, 0, 1, and 2, if I remember correctly. Yes. So far in my form, now I have 3 parts that are correct here. And to get this to be reduced row echelon form, now I need to make that -2 be a 1. So in order to do that, I need to divide everything by -2, which is the same thing as writing, or by multiplying by -1/2. So I'm going to take -1/2, I'm going to multiply it by row 1, and then I'm going to put that as my result in row 1. So if I multiply everything in the first row by -1/2, I got 1, 0, -2, and then I have 0, 1, 2. So for a 2-equation system, doing matrices by hand is really not bad. And now I am in reduced row echelon form because I have 1s in the diagonal and then 0s everywhere else left of that equal sign. Actually, I think that I did this in fewer steps than I did in my other video. I must have been more efficient this time around. The tip that I have for this, the tip when you're working with matrices, is work bottom up. So try to get the bottom the bottom row in the right form and then work your way up. It's faster. To put it in echelon form. So work from the bottom up, because that is more efficient than trying to get the top in the right form and going the other way. So now I've got my matrix, and now is to actually get the solution. So my matrix right now, I have 1, 0, -2, 0, 1, 2. And so that gives me my solutions. So the first row, this is basically my x and my y and my equals. So on the first row, I get x equals -2. And then the second row, that tells me y is equal to 2. So you get a solution of -2, 2. So that is the 2-variable system, and that's using reduced row echelon form as opposed to row echelon form. Do you have any questions on that? Either how I did it, maybe the notation, the thought process on what I decided to do. Any questions there? Okay. Come on. Okay, so now I'm going to go into technology and using technology to solve this, because once you start getting bigger systems, it's a lot more work to do by hand. If you have a small system like this, that's easy enough, but I'm going to demonstrate with technology. So this is the link that I mentioned during my video yesterday. That is my preferred link. So I need to make sure I'm off my pen, so I'm going to click on that. Okay, so first I'm going to use the Row-Echelon form link. So when you have two equations, that means you have two rows. So I'm going to hit two rows, and then number of columns. So I have 3 columns, and then I hit submit. So now I need to fill this in. So I know that it's not on the screen anymore, but just trust me that this was the matrix that I gave. So I'm just literally typing in the numbers in the same form that it is given. So I'll pop that back up there. So it's 2, 6, 16, 2, 3, 7. So 2, 6, 16, 2, 3, 7. So I'm going to hit submit. Okay. And now it's showing all of the steps. I don't care that you do that if you're using technology. So here's what I'm going to demonstrate what you would show if you were doing this on an assignment. So you would first start with your matrix. And then you have an arrow in a row echelon form. So you just write REF, that's row echelon form. And then you would put the resulting that it gives you. So that's the very last matrix it gives us, which is 1, 3, 8, 0, 1, 3. 1, 3, 8, 0, 1, 3. So if you have a graphing calculator, actually REF is a common abbreviation for doing this. And then because this is row echelon form, we still have to do the back substitution. So that you would do by hand. So this is x, y, and the equals. So you would say, okay, y is equal to 3. And then we have x plus 3y equals 8. So then we solve by plugging in y. So that's x plus 3 times 3 equals 8. So x plus 9 equals 8. And then when you subtract 9 from both sides, you get negative 1. And then you would give your answer as negative 1, 3. So that is how you would show your work if you're using row echelon form and a computer. So you would just write ref in between the first two. You have to show the matrix, show your final thing, and then do the back substitution by hand. Now, if you're going to use reduced row echelon form, so again, when you're doing this, you start with your system. And then the abbreviation for reduced row echelon form is literally RREF, reduced row echelon form. It's just the first letter. So now I'm going to go back to that website. I have to hit the back button enough times. And now we're going to do the reduced row echelon form here. So I have 2 rows, 3 columns. Hit submit and then type this in again. Hit submit. And so this last matrix, that's what I'm going to write down. So let's see, it's 1, 0, negative 1, which matches with x. And then 0, 1, 3, 0, 1, 3. And then you would say x equals negative 1, y equals 3, and then give your answer like that. So that's how you would show work if you're using technology, and that would give you full credit by doing this. If you just wrote the final matrix, or you just wrote the answer, but you didn't write this in between, you're not going to get full credit. This is how you're demonstrating what you typed in, what you started with, what you ended with, which method you used via technology, and then you're giving your answer. So that's the work that I expect when you're doing this using technology, when you're solving with either row echelon form or reduced row echelon form, the Gaussian elimination or the Gauss-Jordan. Any questions on the expectations of what to show for that? Okay. So now I'm going to use technology for the rest of this because I want to talk about the different types of systems. So an overdetermined system means that you have more equations than you have variables. Oops. So more equations than variables. It basically means you have too much information. If you have too much information, usually one of those equations is redundant and you still have one solution, or there's so many equations and they can't all be true and you get no solution. So you either have one solution or no solution. So first is x, y, and then this is all going to be what the equal part. So we have two variables, x and y, but we have three equations here for each of these. So I'm going to use the reduced row echelon form so that we don't have to do any back substitution stuff. So I'm going to use reduced row echelon form to get these systems. So I got to hit back. I got to hit back again because now I have 3 rows and I have 3 columns. So that is a square matrix. So I'm going to type in my numbers and just trust me that these are the correct values for the first example that I have. And then I'm going to hit submit. Okay, now I'm going to scroll to the very last, and now we get ones in the diagonal, 0 everywhere else. So this is the identity matrix. So we get 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so let's write down what that means. So we have x, y, and equal sign. So you get x is equal to 0, y is equal to 0, and then you get 0 equals 1 for the last row. So that last row we got 0 equals 1, and that is false. And if you get something that's false, that means there is no solution. So this is an example where you get no, well, that is not how you spell solution. I crossed my L. Let's try that again. So we got no solution, and that happens when you end up with, on the left side, your coefficient matrix, there's no variables left, and then so you have 0 on the left and then a number on the right. Sometimes it's not 1, sometimes it's 5. But if you get something that's false, that automatically means there's no solution. So this was overdetermined, but they don't all intersect at the same place. And if we try to graph this in 3D, actually we don't even have to graph it in 3D. This could be a 2D graph. Let me open up Desmos. Oh, I already have Desmos open, but we don't want the matrix calculator. Let me go to Desmos, because this is x and y, so we can graph this. So you can see that there's no solution here. So 1x plus 2y equals 0 is the first equation. Second one is x plus y equals 6. So you can see those intersect. And then if we add the third one, 3x minus 2y equals 8. So in order for 3 equations to be in a system and be true, they have to all intersect at the same point. But not all 3 of these intersect at the same point. The green line would have to go through like maybe this intersection point for it to be a true system. Or the red one would have to go through the green and blue. The green, the red, and blue all need to go through the same ordered pair. But they don't. So this is no solution because they don't all go through the same point. Now I have a second one here. We have 1, 2, 0. 116, and 360. So I'm going to put that one again. I'm going to do the reduced row echelon form. So I'm going to go put that in our little solver here. So I'll hit back. 1, 2, 0, 1, 1, 6, 3, 6, 0. And now we have 1, 12, a 0, 1, negative 6, and then a row of zeros. So we had 1, 0, 12, 0, 1, negative 6, 0, 0, 0. Verify. Yep. Okay. So now I'm going to put my little thing so I know where the equal sign is. So this tells us x is equal to 12. Y is equal to negative 6. And then we get 0 equals 0, which is true. So that doesn't matter. So that's true, which means that we have a solution. So because we didn't get a contradiction, then we have one solution, 12, negative 6. So when you're solving with matrices, if you end up with your third equation just getting a 0, that means it's an extra equation, it's redundant, and you really only needed the first two. Are there any questions on overdetermined systems? Okay. So the next one, instead of overdetermined, if I can get this actually to open for me, there we go, is underdetermined. So underdetermined means you have more variables than equations. So it's the other way around. More variables than equations. And for this, there is either infinite solutions or no solution. So it is not possible to have one solution if you have underdetermined systems. So these are not square. So we have x, y, and z, and then the equals. So I'm going to do the reduced row echelon form again. And then I'm going to bring up my matrix solver. I have to change my dimensions. So now I have 2 rows and 4 columns. I had 1, 1, 4, 5, 2, 1, negative 1, 9. Okay. And so now I have this final matrix here. 1, 0, negative 5, 4, and 0, 1, 9, 1. Okay. So when I write these as equations, my first equation is x minus 5z equals 4. Then I have y plus 9z equals 1, because that third column there are the z's. So we would solve these for x and y. So I'm going to change to black because I'm running into the green. So we have x equals 5z plus 4 and y equals minus 9z plus 1. So what this means is that z is a free variable because x and y depends on what z is. And so we can do anything for z, and then that will get us a working solution. So what the book does is they replace whatever that variable is with an a. And so they would write their solution as 5a plus 4, negative 9a plus 1, and then write a as the last one, meaning that z, and they use a instead of z, but whatever a is, you can pick a to be 0, that will give you a working solution. Pick a to be 2, you plug it in, that gives you another solution. So your solution depends on whatever that a is, which is the z variable, and then x and y are picked based off of that. So that's how the book writes the solution. So this is infinite solutions because there are infinite numbers that you can plug into A and still get a working solution. And so this would be one that we'd graph in 3D because we have 3 variables. I'm not going to try to mess around with the 3D graphing since it's hard to visualize. So now let's take a look at this next one here. And again, I'm going to do row reduced echelon form. So this one I have 1, 2, 4, whoops, not 45, 4, 2, 1, 1, 2, 1. Okay. And now I have this matrix, 1 and then all zeros, and then 0, 1, 2, 1. So I have 1, 0, 0, 0, 0, 1, 2, 1. Okay. So the first row, that tells me x is equal to 0. So I have a value for x. The second row, it tells me y plus 2z equals 1. So y actually depends on z. So if I solved that for y, then we got x equals 0, y equals negative 2z plus 1. So again, the book likes to use a, so x is 0, so I can just put a 0 there because x does not rely on another variable. But y relies on this z, which we're going to use a, so negative 2a plus 1, and then z, our free variable, is a. So you don't have to have an equation in each spot. You can put an actual number there if they find, oh, x has to be 0. So both of these are systems where there are infinite solutions. I actually tried to find one that had no solution, and every single matrix that I tried kept having infinite solutions. So I was not getting lucky. So I'm assuming it must be very rare to get no solution with an underdetermined system because I could not get a matrix to work. So most of the time, and this is from experience too, most of the time most underdetermined systems have infinite solutions. So do you have any questions on the underdetermined, how we write the ordered pair for that, or what that means? All right. So that is basically it. That was all I had. That goes through the whole 8.1 basically. The biggest thing is I wanted to go through those definitions, wanted to show you how to show the answer it has multiple solutions, and then I wanted to make sure that you knew how to show work with technology and do that so that way you're not missing points or anything on the assignment. So yeah, that's it. Do you have any other questions on anything? I have not finished grading the week 2 stuff yet, so still getting through there. Okay, perfect. Thank you for joining me. I'm definitely going to have to, before I post this video, I'm going to have to re-watch it and make sure all the sound is okay. If not, I may have to do some editing. So this, depending on how that is, well, this may come out immediately or may not. Especially if I have to watch the whole thing and it's 45 minutes. It may be a while. I don't want to think, oh yeah, sounds all good, and then find a spot where it's not. So thank you for joining me and letting me know that the sound was not working or that there was problems. And our next one, I don't have another lesson scheduled, but if there are requests, if you're like, oh man, I really don't understand this section, can you do a live on this? Let me know and I will schedule one. Just in the beginning, good, okay, so I'll watch like the first 10 minutes and see, and then maybe that's the only part I have to redo. So thank you so much. I hope you enjoy the rest of your Thursday night, you enjoy your weekend, and I will talk to you later. All right, bye.